Good morning, my friends. Today I just woke up to look at this. This is from PBS. Today is actually it's the 14th of January, and this came out on the 12th. And it goes back to the arguments about quantum mechanics, which I have been following since there was the word. Now, I have a new theory. Well, it's not a new theory. It's my theory, but it's new to everybody else. It's called electron flood. And what it means is instead of being huge protons and huge neutrons and tiny, tiny, tiny little electrons, there is nothing more than tiny, tiny, tiny little electrons. And as they grow bigger and bigger and more and more and more, they become stable at certain frequencies, at certain quantities and frequencies. But 1837 constitutes a proton. It's not neutral because it has an out of balance number of electrons. 1838 is a neutron. It doesn't have a positive or a negative. There's an equal number. So a proton is positive because it wants one more electron to become neutral. Right? It's not that a proton is one big gigantic plus. It just doesn't have enough electrons to become neutral. Now the electrons, this is an electron, both of these tied together. The electron, which is what we would consider the explosive electron, which nobody knows about this part, so forget that part right now. This is what's considered an electron. Tiny, 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 tiny little particle that is extremely energetic. That's what an electron is. That's what creates electricity, lightning, static. All the charges are created by electrons. Well, they think they're being sucked to positives. Really, it's electrons pushing other electrons. Now, the dark matter is a muon, and that is part of the electron. They're tied together. They're tied together. The only time they come apart is when they concuss. The only time I've seen them come apart is when they concuss in the Venturi. And I will show you this in detail. But I want to go to Schrodinger because this, I'm telling you, I find life now hysterical. 50 years ago, I discounted Schrodinger as being just not, he couldn't possibly be right if everybody else was right, which they weren't. Everybody else was wrong. He's the only one that was right. And look at this. This is hysterical. I was deep into this stuff. This was more, I was deep into this, as deep as you could get. Now, and this is all stuff that I did. I mean, I was so deep into this stuff. But here, this is the one this is like a cheat sheet. You can see it's seen some action. Now, here's Schrodinger. I go down to all the Heisenberg and Hund's rules and Pauli and Aufbau and core electrons and Broglie, but the one I got here is crossed out is Schrodinger. All right, and here's what it says here. This is what I had written down. He got accurate energies for the electrons at the expense of accurate positions. Therefore, his model of the atom dealt with probability. So he was just guessing, is what I'm thinking in my mind, of finding given energies at given positions. He came up with a wave equation, quantum mechanic model, and I crossed it out. Like, this guy's not right. Because everybody else, well, I'm going to show you on here that Schrodinger, anyway, we'll get into that. But I went through Millikan's oil drops experiments, and then we get into all kind of oxidation reduction. I mean, I was deep in this and bonding, and you know, I tried to substantiate the things that everybody was saying. And I really got to be honest with you. I could get down to the point where I could see what they were saying, but nothing made sense to me in the end. And I made that statement to my professor. I said, this stuff's not right. It's just not right. You know, it might work out so that you can see atoms and so forth and say, okay, there's a certain number of particles in a certain atom, but all that is just like a bigger snowball. And they didn't understand that the nucleus of all atoms, right? All of these are atoms. All of these are elements. Every one of these is what's considered another atom. And every one of these has a bigger and bigger and bigger and bigger piece of matter that it controls. But what they think is like that has one proton and one electron. No, it doesn't. It has 1,837 electrons in here. And it probably has 1,838 or more. But it's the smallest particle that exists in an atom form. The smaller particles are these. And you can have any number between 1837 and 1. All right, so you could have 420 electrons in a chunk. That's considered a nuclear decayed particle. It's the nucleus has decayed into, that's what nuclear decay is. It's insane to not understand this. All I can figure is that Einstein was put out there as to destroy science. It's the only thing I can think of. So that we could get ahead of the Soviets or some nonsense. Absolute insanity. Because what he said was just, a 5-year-old or 10-year-old should be able to understand what he said was totally wrong. And I could never prove it until we did the light experiments. And then it's so obvious that it's undeniable, but it's still being denied, although I am seeing a little bit of movement. Oh, we're going to look at this, we're going to look at that. Yeah, well, they started yesterday. I saw one that came out that they're looking into squeezing light, and that's what we're doing. We squeeze the light. That's how we got these particles. All right, I'm going to get your mind rocking if you want to get your mind rocking. If you don't, go somewhere else because it's going to start rocking. Now, I think I showed you the stuff I did a long time ago, and I wrote off Schrodinger. Well, now I am on his team. Now, this is red light from the laser, pulsed, bip, 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 and there's a particle back here, and it controls a wave, just like this does. You see what happens with a magnet? Particles that are electrons are nothing more than magnets. When they flow through the air, you see what happens? You see that thing? You see it's moving all that stuff around it? Well, you can't see it. But it controls a huge region around itself. You see it? You see the stuff moving? As a particle goes through the air, it's pushing or everything is in front of it like this. So you got a particle and you have a wave. It creates a wave. That's what nobody understands. They say, oh, sometimes it's a wave, sometimes a particle. No, it is always a particle, and it always has a wave in front of it because it controls this magnetic region. Simple as that. If you constrict that magnetic region and crush it, this is the effect. And they have just acknowledged this. And yesterday there's this big thing about squeezing light, and I've been showing this for years. And this has really had my attention for years now because I saw light accelerate, obviously. I mean, nobody can deny this. And that's the particle. Obviously, nobody can deny that. And this is the particle that is seen just prior to the concussion at the Venturi, and then these particles separate. Nobody can deny this. And then they say, oh, well, light can't, light, we have a redshift. You say, well, what is a redshift? Well, a redshift means that everything is moving away from us so fast that it's pulling the light with it. I say, wait a minute, that doesn't make sense. I say, oh yeah, that's why. Oh, that's because the universe is expanding. It was a big bang and everything just went boom. And so now the light is shooting at us, but it's being stretched. So if you had a thing that was spinning like this, you're pulling it. Well, as a matter of fact, here it is. The universe is going out this way. Well, normally the light would be spinning this fast, but if the universe is going that way, we see it this way. So that's a redshift. But here on Earth, this is what it would be like. But if we shot it out into space, it does this. Well, guess what? It can slow down too. And they say, and Einstein would say, oh yes, lights obviously can slow down. It slows down in water, it slows down in this and that. But outer space is a vacuum. That's absolute total nonsense. Outer space is completely saturated with light particles, and that's all there is light. It's just that instead of being in a solid mass, they're in a gaseous, dispersed form, but they're the same particles. They're just not as dense. That's all it is. Absolute nonsense what we've been told. It's starting to come to me that not a single thing about physics is right. Not one single word. All right, this is light obviously sped up and slowing down, one or the other. Either they're going faster here, spinning faster and slowing down this way, or going faster this way and concussing and slowing down. I think it's concussing and slowing down. That's my interpretation, but everything is up to, I'll listen to anybody if they can show me. I'm saying this is a right-hand spin, which means the particle would be drifting to the left. We take one picture and it's all these particles at the same time in different positions because it's so fast. Now, it's spread out here and it's compressed here. I say it's spinning to the right, means it drifts to the left, impacting in the space that it's concussing with and crushing the particle closer and closer. That's how I'm taking this. Now we're going to go into what magnetism really is and how it affects the particles that it magnetizes. Because I can take metal, I can take iron, and I'm going to show you, well, let me show you right now. Here's what I'm asking somebody to do. I'm not going to do it myself. I'm done with this doing tests. I want to energize your mind. My mind is so de-energized now it's over. I want to know if particles, about the weight of particles, and we need to do a particle weight test. So you need a balance beam with a fulcrum here, okay? Now, so the balance beam is just going to be an iron bar, just iron bar, non-magnetic iron. As long as you can make it, as heavy as you can make it, is the better. Now, get it completely perfectly balanced. Perfect. No going this way, no going that way. Then magnetize this thing. As magnetic as you can get it, because you can magnetize iron. All you have to do is take a bar of iron and stroke it across a magnet, and it'll become magnetized. Now, the problem is, well, let's continue with this. So now you're going to end up with a positive end and a negative end. Basically, that's the way you would think of a magnet, but I'm not sure it's correct anymore. What I want to know is, will it still balance exactly correctly? If it doesn't balance, it means we've dragged some kind of particles that have some kind of weight, either this way or that way. Then we got to decide, if it doesn't balance anymore, what changed? What's the changes? Did it add electrons here, or did it take the dark matter over this side? Right now, it's all up in the air because there's dark matter all over the place. And these are the dark matter balls, and those are the white balls. And the white balls are the concussive particles, which they call electron showers. And they shower like hell. And those are all electrons. And these are the muons, the black balls, which I think are dark matter. Now, when they concuss, they separate. Before we saw them as the four little particles together. Now, the black ones are going away from the white ones. The white ones explode, the black ones just don't have any value to them whatsoever, it seems. I don't know if they have any weight. I don't know what they do, but I know they don't. All I know they do, for certain, is they attract the white ones. You see them come back together here? When they came in here, they were together. They didn't want to come apart. The only reason they came apart was because they had to come apart to get through. The white ones said, well, this is still a little bit up in the air. Why the black ones get pushed away and the white ones fight each other so much. But these are the electrons, and these are the only ones we ever knew about before. These are the ones we never knew about. They're the muons. They're the dark particles. The CERN knows about them, but they just think they're just like something that's just laying around, and they might be. But they are normally attached to an electron. So an electron is not just a negative particle. It is always, in its natural state, an electron is attached to a muon. That is their nature. And here's what they look like when they separate. All right, the black ball goes on its way. I just showed you the black balls. That's it right there. And that's what happens with the white ones. And they know this. I mean, they know it, but they don't know they're attached together. Because CERN has taken protons, and I just told you, a proton is 1,837 times bigger than the particles we're working with. We're working with light. So they're hitting things and they just got all kind of debris and they're seeing all these things and they just can't figure out what the hell it is because they're starting with too big of an event. That's all. So I'd like to have somebody do this. I'd love to understand. You know, and I'm going to tell you something. Here's what's happened. Here's something funny. This actually could play into this pretty well. I did a lot of things, and one of the things I had to do was get things certified up at the Weights and Measures. And one year, I can't remember, it was long ago, but you had to get them certified every, I don't know, so many years. So I had to take the weights up there, and I went up there. Normally, I used to go up there, and they would weigh them, and I'd leave. And because they'd certify them, they say, okay, that weighs a pound, that weighs whatever it is, grams and so forth. Now, so I give him the weights, and I say, okay, let's go. And he says, no, you got to leave them. I said, what do you mean I got to leave them? I mean, there's a thing right there. Put them in there and test them. I mean, I don't have time to come back. He says, no, it's too cold. I says, too cold? I said, what's that got to do with it? He says, they don't weigh right when they're cold. And I said, whoa, come on, buddy, let's go, let's dig a little deeper into that. And he said, no, you just got to leave them. I got too much to do. I don't want to talk about it. It's got something to do with the cold is falling down. You ever open a refrigerator and you see the cold falling down? We can't get an accurate weight. You just got to leave. So I had to leave. But it always bothered me because, I said, does it bounce around like that? He said, no, they just don't work right. They don't weigh the same when they're cold and when they're hot. I think that's how I left it. It goes a long time ago. And that always bothered me. And now I can understand. Cold is nothing more than electrons have left. They're gone. So they have to weigh something. And when they're hot, you force electrons back in. And I have seen, yes, they do weigh. However, I want to know now, in the magnetic sense, can we drift them from one side to the other magnetically instead of pulling them out of there by heat and cold? So if we can, normally, I want the same temperature, the bar the same temperature, non-magnetic, same temperature, magnetize the hell out of it, and see if it still stays balanced. Somebody can do that, I would love it. Okay, I'm going to just let this play out for another minute or so, and this is, Schrodinger against Bohr, and Schrodinger went on his own way, and he was the one who was right. Now, we need to spend some serious time looking into the bounce mechanism of photons, and literally that's what it is. They have a magnetic field around them which can bounce like that. That's all it is. There's a particle in the middle, but you know how your magnets, you push them, you can feel them push to shove. Well, when they slam into something, they compress. When they do, they give off energy. It's the nature of them. And we're going to go into it deeply, but you got to get deep. We got to look at all, this shows all kinds of energy levels and the way the light is emitted and how fast the pulse is pulsating. I mean, it is a ton of stuff to go over. But let me just finish it up with a couple last statements he makes.
Fundamentally unpredictable ones that would have made Bohr proud. And the difference, well, is to do with how strongly the system is coupled to the measurement apparatus.
All right, coupled to the measurement apparatus. See, they always used to say, well, you destroy something by looking at it. No, the reason you need some photons to be pushed into the system so you can get some light back. When you're working in this realm, you are interfering with the photons that you're trying to look at. That's all it is. It's not that it is when you're looking at it, you're destroying it, but it's not like, that's just the nature of push to shove, which is what I keep saying, but that's all it is. All energy is push to shove.
The weaker the measurement, the less likely a true quantum jump is to occur. But
see, the weaker the measurement, less pushing in, you're not going to make them jump. It's amazing they missed this.
More on that another time. For now, both Bohr and Schrodinger camps have new evidence in their favor. For the longest time, physicists have shied away from asking which interpretation of quantum mechanics is correct. It's considered by many to be a point of philosophical preference, whether you roll the dice with Bohr and Heisenberg in Copenhagen, or ride the continuous and deterministic wave of Schrodinger and others.
I'm going with Schrodinger, and then we're going to go deep into it. I mean, it gets deep. So if you're a geek, come on board. If not, well, that's fine. Go somewhere else. But, I don't make things complicated. It's not complicated. That's the key. It's just insanity. You have to make everything so complicated, make all these different nonsense things. No. It's like two balls bouncing into each other. That's all it is. And if one of them's hard, it bounces fast this way. We're going to get into it. Trust me, I know what I'm talking about on here. I've been doing this a very, very long time. I understand this stuff pretty good right now. And if somebody wants to discuss it, I would love to debate. That's the problem. Nobody to discuss it. Because I'm showing things that they can't really disagree with, so they just stay away. I'm serious. I mean, not a single one will discuss it with me. People that should see this stuff and understand, I'm showing them what they're looking for. So I'm just going to keep doing what I'm doing and just muddle through life. All right, I love you all, and I hope everything starts working out for the better. I'm going to tell you one thing right now. Regardless of all this nonsense, love everything there is in life, my friends. All right, just love everything. If you love everything, you're not going to have violence, you're not going to have hate, and maybe we'll find some peace somewhere. It's a tough time, right? But think of it that way. Think of, and I'm just going to point to who it is. Jesus Christ is the one. He's the only one I've seen in history. And I've been studying history right now very deeply. Nothing but wars. Nothing but wars. Killing, fighting, barricades, bombs, guns, death, hatred. From day one. The only one who came in and said, love everybody, love everything, was Jesus Christ. All right, I just want to make one last statement. I shouldn't mix all these things together. I agree. But that's the way I do things. Everything has a relation to everything else. And if you don't mix things, you're missing so much. When you compartmentalize this and that, you say, oh, that has nothing to do with that. Of course it does. Everything has to do with everything else. But it was a wrong statement to say that Jesus Christ was the only one that was ever speaking about being good. There's a lot of fabulous people. However, as far as I can determine, Jesus Christ was the only one that could do all these miracles that were very, very well documented and prophesized and all these kind of things. They were very mysterious, no question whatsoever. But I am finding that they all held water pretty damn good. So I wouldn't discount them out of hand. And if they are what they claim to be, you better pay close attention. I am. That's what that's my recommendation. Because if they are what they are, this life is like that quick, and the rest can go one way or the other. It looks like to me. I could be totally wrong, but I would consider loving everything there is, and every life, birds, insects, everything. I mean, I hate to kill insects and things. I do. But, when you do, you still have to honor them that they had a life. Everything has a life. The ancients, they used to put dung beetles and mummify them. They mummified birds. They held everything sacred until there was good and there was bad, and the bad took over, the good just left. And I believe they left this planet. That's what my belief is now. You could call me crazy, but I don't think so. I think the people that have been calling me crazy are the crazies. All right, so stick with me or Vayos con Dios.